Let's look at a motivating example. Suppose you work in a manufacturing firm and it is thought that the cooling time influences the impact strength of a plastic material. You carry out a study to measure how cooling times changes the impact strength. The results are shown in the table here. How do you want to determine whether cooling time really affects impact strength? This is a regression problem as we are predicting numerical values and we can use our linear regression to help us. So what exactly is our linear regression? Linear regression is a model that assumes a linear relationship between the independent variable and the dependent variables, and it aims to find the best fitting line that describes the relationship, and it does so by minimizing the sum of the square differences between the predicted values and the actual values. The simplest case of a linear regression is the simple regression where the model uses one input to predict one output. Going back to our example, it is a case of simple regression as we are using one input, time, to feed one output, the impact strength. This model is predictive as once we have the equation of the straight line, we can use it to predict the impact strength for other values of time. But how exactly do we find the best line? Let's look at the three lines here. How do we decide which line is a better fit to the data? In the next part of the video, we will discuss variation of the data from the average and from the predicted line. From there, we will build on the statistical ideas of the sum of square differences to determine how to find the best line. Before proceeding, let's have a brief recap on the straight line equation. In two dimensions, a straight line is given by y equals to a plus b multiplied by x. A is the value of y when x is 0 and it is called the y-intercept. B is the slope of the line. When b is positive, y increases with x. When b is negative, y decreases with x.